Hello, we are team 8.2 of the Mini Drone Senior Design Project. My name is Alexander Magana.
My name is Robert Engler.
My name is Omar Jarquin.
And I'm Tiffany Alvarez.
So today's agenda consists of the background of our project, the project management portion of our project, the technical details that went into completing this project, the assessments of requirements, which shows the testing and risk analysis of the mini drone, and also a summary portion. Tiffany and I are going to be discussing the background of this project. So the background for this project is composed of a MATHWORKS competition that uses an autonomous drone to pick up a Rubik's Cube from a specified location and drop it off to another location. The type of drone that we will be using in this competition is a Perez Mambo drone, which is a quadcopter unmanned aerial vehicle, also known as a UAV, that uses 4 different motors to turn the propellers in order to create lift. A specially designed claw is mounted on the UAV that is designed to pick up the Rubik's Cube. A couple of examples of real-world application where this might be useful is for delivering packages for companies like UPS, FedEx, and Amazon. Some other applications can be for military use, such as surveillance or delivering supplies to troops. They can also be used for agricultural purposes. Now Tiffany is going to discuss the model-based design and the objective.
Model-based design uses virtual representation or simulation to test a product before its final phase. It allows for periodic testing at every iteration of the design process, which saves time and production costs associated with prototyping. We have used model-based design to test both our code as well as our claw design. In these short clips, we can see how Simulink can model the behavior of the drone before the code is ported. This can help us identify issues early on in the process. The objective of our project had 2 main components. The first was to create a Simulink algorithm to autonomously command a drone to take off, follow a designated path, and land in a marker, while auto-correcting any deviations caused by obstructions. The second was to design a drone modification to enable it to pick up a Rubik's Cube from an assigned location and be able to return it to its original departure location without dropping it. And now I'll pass it on to Alex to talk about the project management.
So this presentation was made possible thanks to our sponsor, MATHWORKS, and the Senior Design Program Director is Dr. Michael Thornburn. Jose Luis Perez serves as our group advisor. The team was composed of 4 members, with Tiffany serving as the team's leader. The project was divided into 2 categories, where Robert, Tiffany, and I were working on the Simulink portion, and Omar was working on the cloud design. Our project timeline can be seen here in the form of a Gantt chart. This project was divided into 3 phases, with the first being the conceptual design review. This phase was composed of information gathering and learning how to use Simulink and MATLAB software. The second phase of this project was the preliminary design review, and this was broken down into individual tasks that were required in order to complete this project. Most of the focus of the project went into this phase because it consisted of trial and error and researching different ways to accomplish our goal. The last phase of this project was the critical design review, which involved troubleshooting the individual block sets that make the Simulink code and fixing any bugs that may have occurred in the code during test flights. Also resolving any modifications that were found while trying to install the claw onto our mini drone. A quick breakdown of this Gantt chart: what is seen in green is completed, and what is in blue is in progress. Red is at risk, yellow is pending, and orange is scheduled. Some of the deliverables we were able to accomplish resulted in a full simulation of flight and landing of the mini drone in Simulink. We were also able to 3D print the claw and mount it onto our drone. Finally, we were able to record our first test run of the mini drone using the Simulink code to fly. Unfortunately, due to time restraints, some stuff that we were not able to complete were troubleshooting the mini drone after test flights, flying through disturbances, or detect the object when the mini drone was flying through the air. Now here's Tiffany and Robert to talk about the technical details of the drone.
So this diagram is the image processing blocks that we made. The first 3 blocks on the left are the post-processing for the image. Starting from left to right, we have an image converter, which converts the imported camera image into an RGB. Then a second converter, which converts it into an intensity image. And finally, an auto threshold block, which converts the intensity image into a black and white. The result is a pixel matrix with white as ones and black as zeros. 3 matrices are then extracted from the top left, middle, and right of the image. Each submatrix is summed to determine the amount of white area in each section. The sum from the left and right matrices are compared to constants to determine the position of the drone over the path, and the middle matrix sum is compared to a constant to determine if the drone should land. The output data is then sent to the path planning block set, which Robert will cover on a later slide.
Thank you, Tiffany. This is the control system, which has 3 inputs and 2 outputs. The inputs are data from the reference value server commands, sensors, and vision-based data. These outputs are for the motor commands and flag. The outputs are used to control how the drone responds to its environment and will dictate where the drone moves or ends its flight. As shown previously, the path planning block is a subblock within the control system. The control system is designed to allow the drone to move linearly and rotate in order to conduct turns while following the line. The system takes in data from the ultrasound, gyro, and camera sensors. The sensor data is then fed into 2 charts where they dictate whether the drone rotates and or translates in a certain direction. This chart works in a way that in order to move on to the next block, the conditions have to be satisfied. Therefore, during the hover state, the drone will climb to 1.1 meters of altitude while maintaining its X and Y positions. It is important to note that the value of Z out is a negative. This is because the drone's ultrasound sensor reads the distance from the ground and back as a negative value. After 2 seconds have passed, the drone will enter its cruise state and begin moving forward at a predetermined velocity constant of 0.000562. This simply means that the velocity of the drone will be constant while moving linearly. dx and dy represent small changes in the drone's x and y coordinates based on the yaw and velocity values. This is why those variables are added to the x out and y out in the cruise state so that the drone can continue moving forward at a predictable rate. Once a turn is identified, the drone will begin rotating and maintaining its current x and y positions. The condition that makes the drone decide when to turn is based on the image data provided by the camera sensor. This feeds a true or false value or a 1 or 0 into the state, which turns the block on or off. This process takes about 1/3 of a second for the states to switch between the cruise and rotation states. Once the drone has identified the landing zone, a value of 1 is given to the land variable, and the reduced altitude block is triggered. This block maintains the drone's X and Y coordinates and decreases the Z coordinate. It's important to note that adding a number to the Z out variable decreases the drone's altitude. The values for Z out variable come from repeated simulation testing and were determined to be optimal for the rate of descent. As the drone's camera begins to slowly zoom in on the target, more black pixels are counted rather than white. The pixels are a 1 for white and 0 for black. So based on our image processing data, the land variable becomes 0 when this occurs. This is because the drone's camera is only able to see black pixels, which falls below the threshold that's been defined to set the land condition as a 1 or 0. This is why we have the land state triggered when land is equal to 0. This landing state allows a similar pattern as the reduced altitude state, except the rate of descent is a bit faster. Once the drone's ultrasound sensor obtains a value of greater than or equal to -0.35 meters, the drone will quickly descend itself to the ground, landing on the target. This is shown as the finished state. While this descent is occurring, the drone maintains its X and Y positions. This is important because we do not want the drone moving away from the landing zone once it's been identified. This chart shows How the rotation of the drone is triggered. The chart is fed data from the image processing block, which states whether the right or left values are true or false. If the left is true, then it outputs a value of -1. If the right is true, it outputs a value of 1. And if both are false, then it outputs a value of 0. This value is fed into a switch block and checked with the rotation variable from chart 1. If this value has been determined to be greater than 0, the drone will begin to rotate. The rate of rotation is controlled by the gain block, which can be seen at the bottom of the path planning diagram, and has a value of 0.00456. This value was obtained through simulation testing in order to determine a reasonable rate of rotation for the drone so it would not deviate from the path too much. This data is then fed into an addition block combined with the delay, which is at a length of 1. This is repeated so that the rate of rotation consistently gets a delay signal. Once this has all been done, the data is finally fed into the bus assignment block and sent to the updated reference command port. This concludes the explanation of the path planning diagram, and then I will now pass it on to Omar.
So, in addition to the autonomous flight, we were also tasked with designing a grabber mechanism that would be able to help the drone in picking up and delivering a designated payload. Before we begin thinking about the designs of the grabbing mechanism, we first had to consider the limitations of the drone. An equilibrium analysis was conducted to find a max lift through calculations similar to these here. This analysis concluded that with 110% thrust, the drone could produce 1.556 newtons of thrust, roughly equivalent to 158 grams. These calculations were then repeated using 95% thrust to account for altitude changes and other position changes. The analysis concluded that the drone could fly with an additional 68.5 grams, which led us to the power to weight ratio of 2 to 1. This ratio indicates that at max lift, the motor can sustain twice the weight of the drone. We also found that this ratio of 2 to 1 is a typical ratio of hobby drones. Just for comparison, competition drones have ratios ranging from 8 to 1 to 14 to 1. Once the limits of the drones were determined, we began to consider the payload in the total mass of the drone. This payload varied throughout the project due to the mass limitations of the drone. When the project first started, we were considering a standard 3x3 Rubik's Cube. Due to mass limitations, this changed. The 3x3 cube was not possible because it had a mass of 94.8 grams, which far exceeded the maximum allowable mass. After taking this into consideration, a second option was proposed, this time using the smaller 2x2 Rubik's Cube. While this option had a mass lower than the maximum allowable, it would highly restrict the mass remaining to be used for the augmentations to less than 5 grams. This option was ultimately replaced for the third option, which was the mini 3x3 cube, which only had a mass of 12.6 grams. Given this information, we ultimately decided on the mini 3x3 cube as our designated payload due to its low mass and small dimensions. Once we had determined the payload, the design phase began, which resulted in 2 possible configurations for the grabber mechanism shown in the following slide. When the design phase began, we had one goal in mind, which was to reuse any of the electrical components, simplifying and eliminating any electronic modifications. This resulted in 2 main designs for us to analyze. The primary design was the center of mass design, which had the benefit of the augmentations being symmetric about the center of mass, thus retaining the equal distribution of mass. This would allow for the drone to adjust to the added mass more easily than if the mass was not distributed evenly. This design option, however, would require the relocation of sensors on the belly of the drone, which was out of our expertise and would likely fail due to the complexity of the circuit board and the attached sensors. This led us to the second proposed design, the front-mounted design. Although this design would feature an uneven weight distribution of mass, no relocation of any electronics would be necessary. The changes in mass distribution would ultimately change the inertial values with respect to rotation in all 3 axes. Fortunately, this information was attained through SolidWorks mass properties, which was then forwarded to Robert for him to input into the drone's properties. So due to the far less complex nature of the front mount design, this design was chosen to be further developed and improved upon for the eventual deployment onto the drone. The next step in the design phase was to design a subframe for the grabber to be mounted to, as well as for the landing legs to be attached to. When designing the subframe, our main goal was to reuse already existing mounting points rather than adding more mass into creating our own points. This drone has four circular Lego style connectors on the underside where we intended to connect the subframe to. In addition to this, we had to extend the landing legs out beyond the subframe to create a wider landing surface. This would produce a more stable landing process with regards to the drone tipping. With this in mind, the first iteration of the design was the subframe version 1, which featured four rigid legs directly attached to the extensions made from the subframe. After testing the fitment of this design, we took the required changes and improved on the design, which resulted in the subframe version 2, which featured two landing rails as opposed to four individual legs. This subframe extensions were also changed to cylindrical features in an effort to reduce any additional mass. This design was inspired by the commonly found fixed landing gear of most helicopters. With the changes made, the second version was printed and test fitted and was chosen to be the landing gear for the drone. During the test fitting process, there were other components to the design that were printed as well, which introduced us to the fabrication limitations, particularly the limitations of the 3D printers used. Prior to our first print of parts, we had anticipated issues that would arise from fabrication simply because machines tend to have limitations, especially so when working with parts as small as these. And as expected, there were some issues with the first print that we had to improve upon. The first being the gearing on the grabber arms. Due to the original size, the 3D printer was unable to render them properly. This issue was fixed by cutting the number of teeth in half, effectively increasing the space in between each tooth. Unfortunately, this also led to changes in the worm gear because the original worm gear thread spacing was now too small for the new arm gears. This issue was fixed similarly to the arm gears by reducing the number of rotations of the thread by half, which resulted in increasing the distance in between each thread just enough for the new teeth to mesh properly. Separate to the gearing issues, there was a failure with the motor housing, which occurred due to the overall thickness of the part being too small. This was fixed by increasing the overall thickness of the part, which increased the thickness of the wall of the motor housing as well. All of these fabrication issues were fixed according to the problem, and with the second print, these issues were no longer present. With the grabber components ready for deployment, the remaining process was to analyze the subframe and landing leg components to assure that they would not fail under loading. When analyzing the subframes during a static test, each subframe was subjected to an applied load of 2.5 newtons, which is the equivalent to about 3 times the weight of the drone. This was done to demonstrate their ability to sustain the weight of the drone as well as a mild impact from when the drone lands. For the version 1 subframe, the peak stress was about 8.88 times 10 to the 5th newtons per meter squared, with a peak deflection of 0.15 millimeters. With the appropriate material property of yield strength, we were able to estimate the approximate factor of safety, which is simply defined as the ratio of the material yield strength over the applied maximum stress undergone. A higher factor of safety indicates that the body could sustain higher loads than those applied, while a lower value indicates that the body could endure less applied load before failure. In this diagram, the scale on the right represents the stress undergone under the applied load, with blue indicating lower values and red indicating higher, more critical values, as these are the locations where the part is most likely to fail. Knowing the yield strength of the material, we were able to determine that the version 1 subframe had a factor of safety of 34.7. The same analysis was conducted for the version 2 subframe. Applying the same load and analysis as the version 1 subframe, the version 2 resulted in a peak stress of 1.803 times 10 to the 6 newtons per meter squared, with a deflection of 0.057 millimeters. The same calculation done for the version 1 subframe was repeated to estimate the factor of safety, which determined that the version 2 frame had a factor of safety of 17.1, which is noticeably lower than the version 1. This difference could be attributed to the lower amount of material used in the version 2. In the next slide, I'll summarize the material properties as well as the costs associated with each subframe version. Here we can see a more compact summary of the determining factors when deciding which of the two subframe versions would be the final choice. Although the version 1 has a higher factor of safety, it also had a higher mass, printing time, and as well as the cost per unit. While a minor difference in mass might not affect the drone's flight as much, the differences in printing time and cost cannot be ignored. A difference in cost per unit of 81 cents can amount to a significant value should the components be considered for mass production. Similarly, the difference of 41 minutes in printing time also cannot be ignored, although for mass production, a different manufacturing process such as injection molding might be considered for this. These minor but noteworthy differences were ultimately the deciding factors for choosing the version 2 subframe as the final component to the drone's augmentations. In the following slide, I'll briefly discuss future design improvements. For future consideration of this design, there were some supports added to each leg of the to reinforce the areas indicated as the most likely to fail. With these new supports, the same static analysis was conducted, and it was found that the improvements drastically increased the factor of safety to 70.6 from the previous 17.1, more than 4 times greater than the original version 2 subframe. Minor improvements such as this could prove useful in increasing the structural integrity for increased loads. In the following 2 slides, the final CAD model of the version 2 subframe will be shown alongside the printed version, as well as a short test flight video of the drone functioning shortly after. On the left, we can see the final CAD model of the chosen design, as well as a roughly modeled drone and cube. On the right, we can see a printed final version of the design, fully attached and functional. Next up, we'll display a short video demonstration of the drone and its augmentations being flown to test the effectiveness of the augmentations. It should be noted that when the drone flew out of frame of the, it was because I was too focused on flying the drone rather than paying attention to the recording. Next up, Tiffany will discuss the assessment of requirements.
So I will be talking about the assessment of requirements, beginning with how we have tested for each requirement, then cover risk assessment. Hovering has been tested through simulation and in reality. To verify we have met this requirement, the drone was able to hover over a fixed altitude throughout the path. To test the line follower algorithm, we have tested through simulation and reality, where the drone completed several tracks with different lengths and angles. For the landing requirement, the drone was tested in simulation and was required to land within the marker with an 80% or higher accuracy during the reality test. The drone was also able to fly with disturbances, which was verified visually to see if the drone would redirect itself onto the track. The claw was required to meet mass and stress requirements, which have been analyzed using SolidWorks as well as tested after being manufactured. The drone was able to fully function with the claw augmentation and was also tested visually. Lastly, the drone was able to complete the tracks and landing quickly for the competition by making small improvements after logging times while completing test runs. Some risk we faced when trying to meet our requirements for hovering and line follower were that the drone would behave differently in reality. We will target this issue by testing and calibrating as needed. In landing, impact might cause the drone to bounce off the marker or flip over. We have mitigated this by creating a slow landing algorithm. Printed augmentation parts may break during test flights or the competition. We have prepared for this by having spare parts available. Lastly, in order to compete, the drone must be able to complete tracks quickly and efficiently. For this, we have tested and calibrated our algorithm as needed. Due to the current pandemic, we have kept the plan in case at any point we are restricted access to school. Plan A had some possibility of school access where we would be able to 3D print the claw, test experimentally, and deploy the algorithm in competition. Plan B was strictly remote, where we would not be able to 3D print the claw and all testing would be done through simulation. And now I will hand it over to Alex to cover the summary.
Today, at the end of the spring 2021 semester, our mini drone can fully simulate a flight path and also land on the landing marker. We have also completed our cloud design, 3D printed it out, and mounted it on the mini drone. Lastly, we are able to upload our Simulink code and our mini drone and attempt our first test run. As Omar stated earlier, some improvements could be made in the future to improve the cloud design and make it more durable. Also, some improvements could be made to the simulating code in order to control the thrust produced by the motors, to extend the life of the battery, and also compensate for the added weight the drone is going to fly with. This is the end of our presentation, and we would like to thank you for your time.